Hello and welcome back to Educator.com and welcome back to physical chemistry and thermodynamics. So in the last couple of lessons we've introduced this thing called the constant volume heat capacity, C sub V, and we've introduced this thing called the constant pressure heat capacity, C sub P. Let's see if we can elucidate the relationship between the two. Okay, first of all, know that numerically the constant pressure heat capacity is greater than the constant volume heat capacity. The qualitative reason for that is this. The intuitive reason is this. For a constant volume process, no work is done because the change in volume is zero. Remember, work is pressure times the change in volume. The change in volume is zero, well, the work is zero. Therefore, all of the heat that's transferred during the process goes just straight into the chaotic motion of the molecules of the system. So all of the heat transferred during the process accounts for the energy change. That's why we have that the heat transferred during a constant volume process equals the change in energy. So all of the heat goes to the change in energy. Now, for a constant pressure process, the change in volume is not zero, so work is done. Therefore, the heat transferred in the process, in the constant pressure process, or I should say of the heat transferred in the process, some of this energy that's transferred as heat is used to perform work. So heat goes in, but a part of that heat is used to do work in the expansion, leaving delta U to be less than expected. Thus, the change in energy is equal to the heat transferred, which is similar to this, minus the energy lost as pressure volume work. So the change in energy is going to be less than the heat transferred, whereas for a constant volume process, all of the heat accounts for the energy change. Now, if the change in energy is less than expected, the change in temperature is going to be less than expected, because energy and temperature are the same, essentially. That's what energy is a function of temperature. So if the energy is less, that means the temperature of the system is less. Well, in order to achieve the same unit change in temperature, the same 1 degree increase in temperature, more heat has to be transferred during the constant pressure process. The more heat for the same change in temperature means a higher heat capacity. The constant volume heat capacity, a certain amount of heat is transferred. It's all energy. In a constant pressure process, a certain amount of heat is transferred. Of that heat, some of it is actually used to expand the gas. So my energy is less, my temperature is less. In order to achieve the same change in temperature, I have to put more heat in. So therefore, my constant pressure heat capacity is greater than my constant volume heat capacity. Under conditions of constant pressure, I have to put more heat to achieve the same 1 degree change in temperature. That's what that means. So that's the qualitative reason. So you should be able to qualitatively, intuitively, that's why it's true. Okay, now let's go ahead and do a little bit of work here. Now, for an ideal gas, in other words, let's find out what this relationship between Cp and Cv actually is. Let's find an equation. Now, for an ideal gas, for an ideal gas, it's actually really simple. There are several ways to get this. I just decided to take what I consider to be the easiest, quickest approach. Let's begin with the definition of enthalpy. So begin with the enthalpy is equal to the energy plus PV. Okay, well, for an ideal gas, we know that PV equals nRT, so we can just go ahead and substitute that into that, and we get that H equals U plus nRT. Let's go ahead and take the derivative of both sides with respect to T. So we get dH dt equals du dt equals nR. Well, we know what dH dt is. dH dt is the constant pressure heat capacity, the change in enthalpy per unit change in temperature. Well, we know what du dt is, the change in energy versus the unit change in temperature. This is the constant volume heat capacity. equal sign. Let's keep our equal signs and plus signs separate here. That's our relationship. For an ideal gas, its constant pressure heat capacity is equal to its constant volume heat capacity plus the number of moles times R. Or we can write it this way. Cp minus Cv equals nR. That's it. Now in terms of molar heat capacities, whenever we say something is molar quantity, it's per mole, which means just divide everything by n, divide everything by the number of moles. So when I divide everything by n, what I get is the following. So in terms of molar heat capacities, now this Cp, this is joules per degree Kelvin, joules per Kelvin. When we divide by moles, we get joules per Kelvin per mole, the one we're used to seeing. In terms of molar heat capacities, just divide everything by n. Divide everything by n. What you get is Cp over n plus Cv over n equals R. All molar variables. Just put a line over them. I am messing up all of my pluses minus signs here. Minus, there we go, minus Cv equals R. These are our relations right here. You can think of it this way. It doesn't matter. Anytime you see a line over something, it's a molar. That means that you've just divided everything by n, the number of moles. Okay, there you go. So for an ideal gas, this is the relationship. The constant pressure heat capacity is equal to the constant volume heat capacity plus nR, or Cp minus Cv equals nR. Either one is fine, depending on how you want to use it. Okay, now, in general, if a system has a differential change in temperature that is associated with a change of state, if in going from state 1 to state 2, there is some change in temperature for the system, then Q, the amount of heat transferred, the amount of heat withdrawn from the surroundings, then Q can have an infinite number of values. And this is so because heat, Q, is a path function. Temperature is a state function. If I want to take something from 10 degrees Celsius to 25 degrees Celsius, that's a 25-degree change. I can do it in a whole bunch of ways. I can just go straight to it. I can go up to 100 and down to 25. I can go down to 100, back up to 15, back up to 25. The heat that's transferred is additive. It keeps the heat changes. The temperature itself is a state function. Q is a path function. Therefore, the heat transferred can have an infinite number of values in going from state 1 of one temperature to state 2 of a different temperature. There are a bunch of ways that heat can transfer. The heat transferred can have an infinite number of values. Well, heat capacity is defined as the change in heat per the change in temperature. Well, if the quantities for heat have an infinite number of values, the truth is, for a given change in temperature, there are an infinite number of heat capacities. So heat capacity can also have an infinite number of values. For a particular temperature change, because there are a bunch of paths in order to get from one temperature to another. only two heat capacities are generally important. Heat capacity under constant pressure, heat capacity under constant volume. So when we put these two constraints on there, those are the two that matter, not the infinite variety of them. In other words, we want to go from temperature 1 to temperature 2 under constant volume. We want to go from temperature 1 to temperature 2 under constant pressure. In both of those cases, there's a heat capacity associated with both of those paths, with both of those processes. So only two heat capacities are generally important. But it is important for you to know, again, that heat capacity, there's an infinite number of them, depending on the path that you take, because it depends on the heat transfer. And the heat capacity is defined as the heat transfer per unit change in temperature. Or if there's an infinite number of heats to be transferred, there's an infinite number of heat capacities. CP and CV. CP and CV. There you go. Constant pressure, constant volume, heat capacity. Now, let's go back. So let's return to our mathematics. Let's return to du equals du or dt v dt. Let's see if I can keep all this straight. du over dv constant t dv. Well, we also have du is equal to dq minus dw, which is equal to dq minus p external dv. The definition of work is pressure times volume. So we have our equation, dq minus p external dv is equal to this side. It's going to be du over dt constant v times dt plus du over dv constant t times dv. Okay, now let's see what we can do. At constant pressure,